Okay, so guys, I got up to one part. I got up to here showing you about molar volume. And I wanted to come down and tell you about gas laws. We're doing still notation here. So capital N lowercase a is Avogadro's number, which is 6.022 times 10 to the power of 23 particles, which could be atoms, molecules, ionic units, covalent network units, etc. Okay, so that's data sheet. Molar volume, capital V, capital M, which is also subscript. So that's a subscript. The volume of 1 mole of gas at a certain temperature and pressure. So different temperatures and pressure, it's different amounts. But we tend to use 25 degrees Celsius, which is 298 Kelvin, and 100 kilopascals, which is about 1 atmosphere, give or take a bit. 1 mole of gas will equal 24.79 litres. So we call this standard laboratory conditions, SLC for short. They'll tell you 25 degrees and 100 kilopascals, usually in the exams. At 0 degrees Celsius, which is 273 Kelvin, and 100 kilopascals, 1 atmosphere of gas as well, 1 mole of gas is actually equal to 22.71 litres. So this is showing that, lower the temperature, lower the volume. So standard temperature and pressure, that's the other one that's often used. And you get given both of these on your data sheet. So use your data sheet. Okay, at 0 Kelvin, by the way, which is 0K, capital K, it's negative 273 degrees Celsius. And we're going to see where that comes from in Charles' law. KPA, lowercase k, capital P, lower a, kilopascal. Okay, unit of pressure. Atmosphere, ATM, is also a unit of pressure. And 1 atmosphere is the pressure at sea level, which is approximately 100 kilopascals. Now, I say approximately, we are just simplifying things for you. You get this data off tables. One of the things about pressure and temperature changes in the day, so does pressure. Okay, that's what causes the weather, high and low pressure systems moving around. So I just need you to know that pressure and temperature are always changing, but we just use it as set, okay? And usually 25 degrees Celsius, okay? So the formula, if I want to calculate the molar volume or calculate moles, use this formula. The moles is equal to the volume of that substance divided by the molar volume. So for example, I have 3 litres of gas, hydrogen gas, at standard lab conditions. How many moles do I have? So I have moles of H2 equals our volume of gas, 3 litres, divided by the molar volume. And that gives me 0.121 moles. Now, if I have, instead of the volume, I don't know the volume, but I know I've got 0.35 moles of oxygen gas. What volume will it take up at standard lab conditions? And we do it this way. And so you notice, by the way, my moles here, moles of H2, I use a subscript next to these just so it's really clear what I'm actually calculating. In these ones, there's only one step, it's easy. But when you do multiple level of calculations, you're calculating moles and volumes of multiple different gases and substances. It really helps to do this notation. So tell me what you're calculating, what this is the volume of. So get into the habit. So moles of O2 divided by molar volume, 0.35 divided by 24.79, and we end up with 0.014 moles. Okay. Oh, moles, that's not right. It's meant to be litres. Excuse me for that sec. This is right about when my last recording just conked out. So I had to find another recording thing. It's just fun. Okay, so that's how many volume of oxygen gas I would have if I have that many. Okay. Oh, there it was recording. I couldn't find the recorder. Anyway, now I'm using Screencastify. And anyway, this is all fun. This is just like real life, guys, like you're in the classroom. Okay, so that's molar volume. Now, I'm doing all these really quickly because I want you to actually go back to this worksheet here and do the work off